Today we'll be doing part 2 of the last lesson using fundamental identities. As a reminder, these are some of the fundamental trigonometric identities that we've been using so far. We have the reciprocal identities, the quotient identities, and the Pythagorean identities. This group of identities happens to show up a lot more than some of the other ones, so I've kind of put them together in one box. And then I've got some other ones, the cofunction identities and the even and odd identities that don't show up as often but do occasionally. So I've put them in their own separate box here as well. So let's talk about other things that we can do with these. One of these is continuing with our factoring. So let's say that we've got factor secant squared of theta minus 1. So a lot of pre-calculus and calculus and beyond from this point is going to be doing what I like to call opening up your toolbox and kind of figuring out what tools you've already learned in previous math classes that you can use to help you out. Because a lot of the problems that you'll be doing are similar, however, they kind of use different steps, or they use these different theorems or tools or rules, etc., etc. And so one of the things that you'll have to do here is recognize that all the way back from factoring, back in like algebra 1, that this is a difference of squares. Secant squared is a perfect square, because if I take the square root of secant squared, I get secant. And 1 is a perfect square. If I take the square root of 1, well, I get 1. And a difference of squares, let's write that down. Difference of squares has the following pattern. If I've got a squared minus b squared, so one perfect square minus another perfect square, secant squared minus 1 squared, which is 1, then this factors to a plus b, a minus b. Well, the square root of a squared, square root of secant squared is secant, and the square root of 1 is 1. So this will end up being the secant of theta plus 1 times the secant of theta minus 1. We could also have something like this. Factor 4 times tangent squared of theta plus tangent of theta minus 3. Well, as it is, this looks fairly difficult. We've never done something like this before, where we've got a factor, a bunch of tangents here. But if I just think of this as, well, what if I think of tangent of theta as x? If I do that, then this is 4x squared, tangent squared, plus x, tangent, minus 3. Well, this is something I've factored before. This will use our a equals 4, c equals negative 3 method. And that's where I list all of the factors of a, so all the factors of 4, 1 times 4, 2 times 2, and all the factors of negative 3. So this would be 1 times negative 3, 3 times negative 1. Since a is not 1, I should also list these in reverse. So negative 3 times 1, and then negative 1 times 3. And then I've got that trick where I'm trying to find the middle. I'm trying to find b, which is 1. And how I do that is I pick one of these factors of a and one of these choices for c, And I kind of put them all in one row. So, for example, if I do 1, 4, just the first one here and the first one here, 1, 4, and then 1, negative 3, I multiply the outer 2. So 1 times negative 3 would give me negative 3. And then 4 times 1 is 4. Oh, that actually happens to be what we need. 1 times negative 3 is negative 3. I put that over to the side. 4 times 1 is 4. And then if I add those together, negative 3 plus the 4, that matches positive 1. So instead of doing a bunch of guess and check where you had to do boxes before, then try to multiply through the boxes to see if you get back the exact same thing, we can just use that. So let's say that wasn't the right choice right off the bat. I would have to try another one. Let's say 2, 2, and negative 1, 3. I'd put those 4 numbers kind of together, and I'd go the outer 2. 2 times 3 is 6. 2 times negative 1 is negative 2. And then I would add that together. 6 and negative 2 make positive 4. And I'd see if that matches the middle. In this case, we got that first try. 1, 4, and 1, negative 3 means that this would factor to a set of 2 binomials. 1, 4 means x here and 4x here. And 1, negative 3 would be plus 1 on the left and then minus 3 here on the right. But that's not actually my final answer here, because at the beginning of this, to help me factor this, I thought of tangent squared, or tangent of theta, I should say, as x. So 4 tangent squared of theta became 4x squared, plus tangent of theta became plus x, and then still this minus 3. So I want to convert that back. Now that I've factored this with x's, I'm going to, again, think of tangent of theta as x, and put back x is tangent of theta. So this is tangent of theta plus 1 times 4 tangent of theta minus 3. Okay, other things we can do. Let's go back to simplifying. Last time we simplified a few trig expressions. Let's see what else we can do today. So we've got simplify starting with sine of theta plus cotangent of theta times cosine of theta. And last time we said convert everything to sines and cosines, because once I have everything in sines and cosines, I can see if there's anything that divides out. Maybe that helps us out in figuring out what's left, and then from what's left, seeing if there's a shorter way of writing that. So sine is obviously already in sine or cosine. Cosine is already obviously a sine or a cosine, but cotangent isn't. So if I look back at my quotient identities, cotangent is the same as cosine over sine. So this is really going to read sine of theta, and oftentimes it helps to write these as fractions. So I can say sine of theta is sine of theta over 1 plus cotangent, we just said, is cosine over sine times another cosine. So another cosine here over 1. Okay, how does this help us out? Well, let's multiply this through. So this will be sine of theta over 1 plus top times top. So cosine times cosine will give me cosine squared of theta over sine times 1 is sine. And if I were to try to add these together right now, I wouldn't be able to, because if I consider this as a fraction and this as a fraction, they have different denominators. In order to add these together, I need to have a common denominator. So it looks like, since this is a 1, I can just multiply this one here by sine of theta. So 1 times sine should give me sine. So I'm going to multiply this by a sine of theta on the bottom here, but I also need to do that on the top. Really, sine over sine is just 1. So I'm going to change the way that this fraction looks without necessarily changing the value of it. Okay, what's this give me? Sine times sine. So this is sine squared of theta over sine of theta plus, nothing changed here. This is cosine squared of theta over sine of theta. So let's go over here. Adding this together now, sine squared plus cosine squared, I'm just going to write that as sine squared of theta plus cosine squared of theta. But now I can just write that as one fraction over, these now have a common denominator, so this will just be that same denominator, sine theta. All right, then I have to go back to my identities again and go, is there anything else I can do? Whenever I see sine squared of theta plus a cosine squared of theta, really any two trig functions that have a squared, and I'm either adding them, subtracting them. Maybe I've got one trig function that's squared and then a 1, so either +1 or -1. Oftentimes I want to look at my Pythagorean identities and see if there's anything there that'll help us. And one of those Pythagorean identities happens to be sine squared plus cosine squared equals 1. So this sine squared plus cosine squared, the top part of this, is just 1. This is the same as 1 over sine of theta. Which lastly, 1 over sine of theta happens to be, looking at my reciprocal identities, cosecant. So this whole thing, sine of theta plus cotangent of theta times cosine of theta, this whole thing, after a bunch of simplification, ends up being the exact same as just saying cosecant of theta. All right, then one of the other things that you might have to do is rewrite some expression such as 1 over 1 plus sine of x so that it is not in fractional form, meaning I want to say what this is the same as without using any fractions anywhere. And ironically, what's going to happen here is I have to use a whole bunch of fractions to get us to a point where I can get rid of all the fractions altogether. And problems like this, you kind of have to think outside of the box. So what do I have here? I've got 1 over 1 plus sine of x. What I'm going to do, and it's not necessarily intuitive to you right now, but as you do more problems, as I mentioned, you'll start to develop that toolbox and recognize patterns where you can go back to that toolbox and go, okay, I can pull this out of here and use this to help me out. One of the things that, like I said, not intuitive, I'm going to take this 1 over 1 plus sine of x. Let me rewrite it here. 1 over 1 plus sine of x. I'm going to multiply this by 1 minus sine of x over 1 minus sine of x. So again, this is just 1, right? 1 minus sine of x over itself is going to be 1. Now, why would I do that? Let's see what this gives me. The top part is, well, 1 times this, that's just going to be 1 minus sine of x. So I've got 1 minus sine of x on top. This is over something. Now to multiply these two on the bottom, I can use a box. And I can say 1 plus sine of x and 1 minus sine of x. Well, when I multiply these, 1 times 1, that's going to give me 1. 1 times negative sine of x, so negative sine of x here. 1 times positive sine of x. And then sine of x times negative sine of x, that's going to give me negative sine squared of x. Where combining like terms, positive sine of x and negative sine of x, those subtract out, leaving 1 minus sine squared of x on the bottom. Now, how is that helpful? Well, going back to the Pythagorean identity that we just used prior to that, let me separate this out a little bit. I know that sine squared of x plus cosine squared of x equals 1. So like I mentioned, anytime I see two trig functions, they're added together or maybe subtracted, I've got both of them squared, or sometimes a 1 with a plus or minus, a trig function squared, I want to be thinking, is there some kind of Pythagorean identity that's happening here? Is there something I can use? Well, if I subtract sine squared from both sides, from this Pythagorean identity, let's do that. Subtract sine squared of x from both sides. These subtract out, and I find that cosine squared of x is equal to 1 minus sine squared of x, which is exactly what we have in the denominator here. So I can use this identity, this Pythagorean identity that I've manipulated a little bit here to find that this denominator is really going to be cosine squared. So I've got 1 minus sine of x over cosine squared of x. Which this is still a fraction, so I'm not done yet because it says not in fractional form. So what else can I do? Let's break this up. This is the same as 1 over cosine squared of x. Okay, and then minus sine of x over cosine squared of x. So I'm just breaking that up into two fractions now. And I can keep going. I can say that this is the same as 1 over cosine squared of x minus, let's break up the cosine squared in this fraction and say that this is sine of x over cosine of x times 1 over another cosine here. Right? Because sine of x times 1, that would just give me sine of x here. Cosine times cosine, that would give me the cosine squared for this one. Then finally, I can say 1 over cosine. If this were just cosine, 1 over cosine would be secant. So 1 over cosine squared would be secant squared. This fraction is secant squared of x. And then I've got minus, what is sine over cosine? Using my quotient identities, I see that this is tangent of x times 1 over cosine again is secant. Now, it's no longer in fractional form. I've got the exact same thing here without using any fractions, which, again, it's not intuitive, but I had to use a whole bunch of fractions here in order to get to that point. The last thing I want to talk about is some substitution. So trigonometric substitution. We're going to use substitution x equals 2 times tangent of theta, where 0 is less than theta, less than pi. We'll see if that matters here. To write the expression, the square root of 4 plus x squared as a trigonometric function of theta. Okay, so what does this mean? Let's rewrite 4 plus x squared, the square root of 4 plus x squared over here. So the square root of 4 plus x squared. All right, what is this having me do? I want to use the substitution x equals 2 times tangent of theta. So what this is saying is I'm starting with the square root of 4 plus x squared, and instead of x here, I'm going to replace x with 2 times tangent of theta. So this is now going to be the square root of 4 plus, instead of x, we've got 2 times the tangent of theta. Okay, that whole thing squared. Okay, so this is the square root of 4 plus, I've got 2 times tangent of theta, that squared, then that's the same as saying that this is 4 here plus 2 squared times tangent of theta squared. So this is now 4 plus 2 squared is 4 times tangent squared. Well, that's just going to give me tangent squared of theta. Okay, now on the inside of this, I've got 4 plus 4 tangent squared. I recognize that I can pull a 4 out to the front, not the front of this entire square root, but the front of what's inside here. So I can pull this 4 out to the front and say this is the same as 4 times, so it's really dividing both of these by 4 and writing what's left, 1 plus 1 tangent squared, or just tangent squared. All right, then I take a look at my identities again, because I've got a squared here. I've got some trig function squared with a 1, so 1 plus tangent squared. Looking at my Pythagorean identities, I've got a different Pythagorean identity that I could use here. 1 plus tangent squared of theta appears to be the same as secant squared. So this is the square root of 4 times secant squared of theta. And then, because I'm taking the square root of two things that are multiplied together, I can break that up into 2 separate square roots. This is the same as the square root of 4 times the square root of secant squared. Well, now, just take the square root of each of these individually. This is the square root of 2, or this is the square root of 4 is 2, times The square root of something squared is just that something, so the square root of secant squared is secant. So the square root, when I started out, the square root of 4 plus the quantity to tangent of theta, that whole thing squared. After all this work here, this is the same as just saying 2 times secant of theta. So there are lots of things we can do with our trig identities. This is just some of these things, and the idea here is to help develop, as I mentioned, that toolbox so that after you do more and more of these problems, you start to recognize patterns and are able to see which tools you're going to need for the job. Open up that box and grab the right ones, so that way you're not just, staring at the problem, kind of fumbling around and wondering where to start.